Specific heat of a diatomic gas. Consider an ideal diatomic gas such as nitrogen at an absolute temperature T close to room temperature. This temperature is sufficiently low so that the molecule is always in its lowest vibrational state, so we don't consider vibrations, but is sufficiently high so that the molecule is distributed over many of its possible rotational states. Use the result of problem 4.23 to write down an expression for the mean energy of a diatomic molecule in the gas. This energy should include the kinetic energy of its center of mass motion and the energy of rotation of the molecule about its center of mass, and use this answer to find the molar specific heat at constant volume of an ideal diatomic gas. What is the numerical value? So we're going to go back to problem 4.23 to take a look at the results that we have. So in problem 4.23, we were talking about mean rotational energy of a diatomic molecule. It has energies given by h bar square jj plus 1 over 2a, where a was the moment of inertia of the molecule about the rotation axis. And this was a degenerate case. We had 2j plus 1 distinct possible quantum states corresponding to a given j value. So we write the partition function for a degenerate gas from j equals 0 to all possible values, 2j plus 1 e to the minus beta ej. And we have approximated the summation with an integral and found that the partition function was 2a kt over h bar square. And by taking the derivative with respect to beta minus del ln z del beta, we have obtained kt. So let me note these results in our problem here. So 500, okay, so 5.21. So we have for this gas the energy levels given by h bar square j plus 1 over 2a for rotations. This is for rotations. And we also have the energy for translations of the center of mass, that remember h bar square n square pi square over 2m, sorry, h bar square pi square over 2m and x square over lx square plus ny square over ly square plus nz square over lz square, etc. This was the kinetic energy of translations. This is rotational kinetic energy of the gas. Okay, so corresponding to these rotations, we have written the partition function sum over j all possible values 2j plus 1 degree of degeneracy e to the minus beta e as a function of j, and then we have obtained our partition function which was so let me remember what it was. It was 2a kt over h bar squared. So let's go back to our problem. So 2a kt over h bar squared, and from this we found the rotational mean energy as minus del ln z del beta, which was kt. And for this one, if you remember, the mean kinetic energy of the translational kinetic energy of the center of mass is 3 over 2 kt. So this is something we have done before also. So therefore, the total energy for temperatures close to the room temperature will be kt plus 3 over 2 kt, which is 5 over 2 kt. So the mean energy per particle will be epsilon bar rotational plus epsilon bar translational, which is 3 over 2 kt plus kt, which is 5 over 2 kT here. So that's the answer to part A. Now part B asks me what is the molar specific heat. Well, for molar specific heat, I need to look at the total energy for 1 mole. So I have for 1 mole 5/2 Avogadro's number of molecules, NaKT, and remember Avogadro's number times Boltzmann constant is known as the universal gas constant R, so 5/2 RT. Therefore, CV is equal to del E bar del T for 1 mole with all external parameters fixed. This would be equal to 5/2 R. The universal gas constant has a value 8.314 joules per mole Kelvin. So this would be 20.8 joule per mole Kelvin. So that would be the numerical value of CV. And it is equal to 5/2 R for a diatomic gas for temperatures close to room temperature. Okay, so we're considering an ideal diatomic gas. We're taking into account the rotations and translations of the center of mass and rotations with respect to the center of mass axis. And for the rotations, we have from quantum theory a degree of degeneracy 2j plus 1. So for the partition function, we have 2j plus 1 times e to the minus beta ej, and which we have shown in problem 4.23 to give us a partition function of 2a-kt over h bar square and mean energy, which is found by taking the derivative of ln z with respect to beta with a minus sign, giving us kt. So the vibrational states are in the lowest possible vibrational state, so we don't have any contribution from vibrations. We have rotations plus translations, 5/2 kt per molecule. And for 1 mole, we have 5/2 Avogadro's number kT, which is 5/2 RT, because we remember that universal gas constant R is Na times K. And the molar specific heat is just the derivative with respect to temperature, which is 5/2 R. The numerical value for R is 8.314. So if we substitute this, we obtain 20.8 joules per mole Kelvin for the molar specific heat of the diatomic gas.